Hi everybody, and welcome to the seventh video in the series TensorFlow Basics with Hemant, and that's myself. In the last video we discussed TensorFlow's high-level API, which is named as Keras, and we also saw that layers are building blocks that are used by sequential and the functional API to build models. So in this video, that is the seventh video in the series, we are going to explore a few questions about Keras core layers. And to be more specific, the questions are like how we can accept a variety of inputs in Keras using Keras input layer, how we can change the shape of the given input if that is required, and then how we can create a set of neurons that is basically layer that connects to a given input, and what will be the output of the layer and its shape after passing through all these neurons, right? What is the concept of an activation and how to choose a specific activation, and what are some of the ways to regularize the output of a given layer so that the model does not overfit? So these are the questions that we are going to explore, and as usual there will be notebooks to actually see some demonstrations around these concepts also. So let's get started. So the first thing that we are going to be talking about how we can accept an input in the Keras, and there is basically an API which is called as tf.keras.input, which allows us to accept a variety of input, variety of the shape of inputs in Keras. So just to take a simple example, as you can see here, so it is input, and one of the attributes to this particular call is shape, and the shape, the value that that we see here, 32 dimensional single dimensional vector, that indicates that the expected input will be batches of 32 dimensional vectors, right? So whatever we define here, that excludes the batches. So for example, let's say if you have 32 features, okay, for a machine learning uh, to solve a particular problem, then what we can do is we can define a vector of say 32 features, and then we can feed in the multiple samples of that particular uh, type of data. Okay, so the shape of this input can also be none. That means if we do not know the shape, we can say that we do not know, or if we know the shape partially, we can say that as well. Okay, so the input then is going to be fed into the dense layer using a functional API or just using a sequential API. Okay, the next layer that we want to quickly talk about is a flatten layer. So it is tf.keras.layers.flatten. Now the purpose of the flatten is actually when we are taking an input, say for example if we are taking an image 32 pixel by 32 pixel into 3 color channels, and we want to feed it to further dense layers, what we need to do is actually we need to flatten it, right? So we need to make it a one dimensional vector. So that is what this flatten is going to do for us. Okay, so the shape, if we are checking, is 32 into 32 into 3, that is 3072, and the none specifies that we do not know size of the batch, and the size of the batch has been defined as none in this particular case. Okay, so flatten will allow you to convert a specific shape into a one-dimensional vector, okay, which can be further connected to the dense layer. The third type of layer that we want to discuss is a reshape. So reshape is basically it will allow you to change the shape of the input. So input shape is, say for example, 12 comma, then we can reshape it into 3 into 4 because 3 into 4 is once again equal to 12. Okay. The fourth layer, and which is a very important layer to understand, is a dense layer, right? So what is the output of the dense layer? The dense layer actually is a matrix dot product of input and the kernel, that is the matrix of weights. Input and weights are going to be multiplied. Matrix multiplication of these two is going to be done, plus the bias vector is going to get added to it. And once we have this output produced, that is going to be passed through an activation function, and we will see what that activation function is in the next couple of slides. But for now, we just understand that we do the matrix multiplication, add a bias vector to it, and pass it through an activation function, and we get an output of the dense layer. So dense layer is can be created using tf.keras.layers.dense API. The first parameter that we give is actually the output dimensional space. So how many outputs we are going to have from this layer, and then we can specify the activation, and then there are a couple of other parameters also, like kernel initializer. So there are different weight initialization options that we have. The same thing for the bias initializer. So there are other options also, like uh, regularization function, and other options are also there. The input to the dense layer is actually batch size into input dimension. The output is going to be batch size and units. Okay, so the conversion from the batch size input dimension to batch size units, that is what happens through the kernel, right? The shape of the kernel is going to be such that the batch dot size dot batch size input dimension is going to get converted into batch size units, and units is this number that we give here. Okay, now since we were talking about the dense layer, it makes sense to discuss about the activation functions. So activation functions are meant to bring in the non-linearity into the output of a neuron, and that is very important because otherwise the neural networks will not function as they function, uh, because in that case otherwise we'll only have the linear relationship between the input and output, and that is not good enough to train the neural networks. Okay, so we have variety of activation functions. So a couple of them which are most frequently used: the linear activation. So whatever is the input, that is the output, that is a linear activation. The sigmoid. So sigmoid basically, so this is the input axis, right? So when we increase the input, the output increases, but it saturates to a value. So it saturates to 1 and saturates to 0 in this direction. Tanh, instead of saturating to 0, it is going to saturate to -1. So it fluctuates between -1 and 0. It acts between -1 and 0 as we change the input. And there are certain issues with this sigmoid and tanh, and we will talk about it slightly later. But for now, to take care of those issues, the ReLU, that stands for rectified linear unit, that is what was kind of invented. Now ReLU actually has a output which goes linearly with the input when the input is positive, but when it is negative, it basically clamps to 0. Okay, so that is rectified linear unit, or ReLU as we call it, and the ReLU actually solves a couple of issues which are uh, which occur when we use sigmoid or tanh functions. Okay, There are a few more activations. So linear activation we talked about. We'll take some specific example here. So let's say this is the input vector, input tensor. So -3 to 3 and a couple of values in between. And when we are applying a linear activation to it, we get the same value. Whatever is the input, we get the same as an output. What if we apply the sigmoid? So we have a tensor which is varying for -20 to 20. So what's going to happen? The negative values are going to get clamped to near 0 values, and the positive values are going to become like close to 1. Okay, so this is a 1, right? 20 is corresponding to 1 in this particular case. What is happening in case of a rectified linear units? Now this value, these are the negative values, right? So they are becoming zeros. This 0 remains 0 and the positive values remains as they are. Okay, and we also have some more control over it. So say for example, if you give alpha as 0.5, the negative values are going to be like reduced by certain factor actually, rather than directly reducing it to 0. Okay, there are a couple of other options also. I'm not going to get into all the options, but just understand that rectified this ReLU is basically for the positive region it is like a linear activation, but just for the negative values is going to act like 0 value. Okay, one more activation, or rather two more. So I'll start with the tanh. So tanh activation is like -1 to 1 the output. So input is say -3 to 3. Here we can see that here it is going towards -1, and in this case it is for 3 is basically corresponding to 1 here. And the softmax activation, so when we are doing the multi-class classification, we need softmax activation in the last layer. And what this does is actually, if we are giving it a tensor, is going to give us a probability distribution, right? And the probability distribution means that the sum of all the probabilities is 1, right? So here if you see all these three values, the sum of them is going to be 1. Okay, and this is a clip of the code which shows how this actually works. So essentially, when we are taking these vector values, we sum up this and then E divided by E sum. That is what is the activation, is the probability for each one of these values which are provided as input. So this is an input. We take the exponential of it, exponential of that vector, which is E, and then we do this calculation, and this is how these probabilities are calculated. Okay, so these are the different activation functions which bring in the non-linearity into the output. Now coming back to the issues with the sigmoid and the tanh. So one of the problems that we saw was actually both of these sigmoid and tanh functions, they saturate. So what it means is when we are near this region actually, even if when we are changing the input, there is not going to be substantial change in the output. So the same case for the tanh also. When we are into this particular range, like when we are out of the range, when the values are changing, then it is going to saturate to certain values. Okay, the amount of the error decreases because of this, especially when there are additional layers added to it, and that basically gives rise to a vanishing gradient problem. Okay, and which is not good, because in that case our network won't be able to learn beyond a point. Okay, so ReLU actually was invented for this particular issue, and ReLU, as we know, there is no limit to the output of it, because if the value is positive, you're going to get whatever is input, that's the output, right? So it doesn't saturate, at the same time retaining property that it is a nonlinear function, because the negative values are, when the input is negative, the output is negative. Okay, so it solves a couple of problems. The ReLU activation as compared to the sigmoid and tanh. Okay, now also there is another factor which is kind of linked to these activations and vanishing gradients, or kind of, faster training, which is initializers, so weight initializers. So when we begin the training, actually the weight values have to be initialized, or to some values, right? Now they could be initialized to all zeros, all ones, or there could be like normal distribution, or there could be like a zero mean standard distribution. Different variety of the schemes are there, and they have an impact on basically, how quickly the training is going to be performed. It has an impact on the performance of the training, in short. Okay, and also there are a couple of things. So for example, if we have the tanh activation, usually Xavier initialization is chosen to work with it. If we have the ReLU activation, we choose like he initialization with it. And a couple of things, couple of rules actually, which drive these decisions is, we want the mean of the activations to be 0, on a layer, and the variance of the activations throughout the layers. Like if you have multiple layers, then we expect the variance of the activation should stay the same across every layer. Now these are the things which are going to drive some of these decisions as to which activation, which initialization we are going to choose. Okay, so just keep this in mind, that they have kind of linked to each other, activation and the weight initializers. And usually when we are with tanh, we go with the Xavier. When we are with ReLU, we go with he initialization. But obviously you can change it as per your problem. Now coming to the overfitting of the model. So there are two approaches that I'm going to discuss. So one of them is dropout. That means some of the activations which are produced by the earlier layer, they are going to be turned to the value of 0. Okay, and how many of them, that is decided by this attribute of the dropout layer. So there is a layer called as a dropout layer, and when we set it to some value, then it is going to drop out that percentage of the activations to 0. Okay, and that helps in basically avoiding overfitting. Okay, another approach that we have for the accelerating the training process and also stabilizing the training process is to do batch normalization. Because what can happen during the training is the output of certain layers, they can explode. Okay, and what we may have to do is basically bring them back to the same kind of range. Okay, so if you are applying the batch normalization, it is going to uh, basically have a, it will try to reduce the mean to 0 and standard deviation close to 1. That is what the batch normalization does actually, and we will see this working in practice. Okay, now before we actually get into the summary for this particular session, let's quickly run through all the different examples. So here we are going to start with the import. So we'll first discuss a bit about the layers. So here we are trying to discuss an input layer, So as we saw, it has a shape here. It is 16 comma, that means one dimensional vector of 16 elements, and batch size is none, and we have another dense layer to which this input is connected. And if we summarize this particular model, let's see, so if we summarize this particular model, we see the output as none comma 2. Why 2? Because the outputs here are 2. And why none? Because the batch size is none actually. So this network is going to take the batch of inputs which is of the shape 16 comma, that means 16, like a one dimensional vector with 16 values in it, and then it is going to produce a batch of so whatever batch size we give, comma 2, because that's the output. Okay, and the parameters, as we can see, parameters are weights actually, right? So how many weights are there? So since we are connecting 16 inputs to 2 outputs, so 16 into 2, right? Each one of the connection is going to have a weight, so 32. And what about, why it is 34? Because there is a bias, and bias is equal to the number of units that we have. So each of the neuron that we have will have a bias. So 32 plus 2, that is 34. Okay, now we have defined a network here, but we haven't given an input to it. So let's give an input and check this out. So what we are doing, we are creating a tensor which is of the shape 116, and we are passing it to this model. Okay, so let's do this. So we are just giving one element, okay, of a 16, like a one dimensional vector of 16 values, and this is what we get, right? So we get one element of 2. Why 2? Because the output is 2 here. Okay, so that's what it is. Now let's see, if I change this to, say, for example, if I'm giving 5 batches, what do I get? The same model. I haven't changed the model, right? I have just changed the input here. The shape that I get is 5 comma 2. So I'm giving 5 inputs, and for each of those inputs I am getting an output which is of the size 2. Okay, so that's what we see, five outputs with a shape of 2. Okay, now let's extend this to a, so here this was a one dimensional input, right? Now here, let's say if I have an image, okay, so which is 32 pixel by 32 pixel into 3 color channels, batch size is none, and output is once again the same. Okay, so let's define this particular model here. Okay, so we see that the output is none, 32 into 32 into 2. Okay, now let's give an input of one of this image to it, and let's check this out. So there you go. So we had this 32 comma 32 comma 3 input, so that's what we gave here, one batch of it, just one like a sample, and this is what we get. So one sample, 32 into 32, and this last axis is being replaced by the output, which is 2 here. Okay, so say for example, if I make this as a 5, we'll check the shape of the output, which is 5, 32 into 32 into 3. Now if I change this model to, say for example, 4, okay, so I'm going to compile the model again, and let's give this input again. What do we get? Let's check out the output. So it's 5 into 32 into 32 into 32 into 4, because now the output has changed. Okay, so I hope this idea is clear, because this is a very important idea to concept to understand, because how to give input is question that comes very first when we are defining our neural network. Okay, now having understood the input, let's talk about the dense layer. Okay, so we are taking in the input as a 16 one-dimensional vector. Okay, a 16 element one-dimensional vector, and then we are connecting it to a dense layer because it's a sequential model. Okay, so this has got 32 units. Okay, so 32 neurons, and it has got an activation here. Okay, now, and then there is another dense layer, and we are going to create a plot of that particular model. So let's see how this goes. So why the output shape is none 32? Because this was our final output here, 32, and the batches of input we do not know, so that's why it is coming as none over here. Now let's plot this model by using Keras.utils. So this is how it is going to show up. Input is 16 element vector, and then we are connecting, so this output is an input to this layer, and then we get this output which is 32, and then we give this output as another subsequent level, and this is where we get an output here. And the same calculation, so number of for the parameters, inputs into outputs plus biases, so that's going to be the parameters as usual. Okay, flattened layer, as we discussed, you know, if we are giving an input and we apply a flatten to it, then we are going to get a one-dimensional vector. So let's execute this. This is what we get. If we are just plotting this, this is what we are going to see. 32 into 32 into 3 is going to get converted to none and 3072. Reshape, reshaping the input. Say for example, if you have like 24 elements here, it can be reshaped into say 6 into 4. So we get like 6 into 4. We can have, say for example, 8 into 3 also. That's also going to work. Right, now here we have a dropout layer. So for example, I'm going to drop out say 50% of the neurons. So first what we are doing is we are generating a data, and then we are applying this dropout to it. Okay, so the first print is data and then the dropped values. So these were the values because it was np.range 10, so 0 to 9, and then some of those values are being 10. So this value has been dropped, second, third, and then fourth, and probably this is the fifth value that was dropped. But what it does is actually it adjusts the other values. So say for example, instead of 5 it made it 6, instead of 7 it made it 14, instead of 8 it made 16, and also it will maintain the sum. It will not change the sum, but it will drop the values. The batch normalization, so we are defining a dense layer here, and then we are applying a batch normalization to it. So we are feeding in the data to this layer 1, and then to this output y we are applying the batch normalization, and then it is is going to standardize the output, so mean 0 and standard deviation of 1. That's what is going to happen. Okay, so that's the quick summary of all the layers that we have. These are the core layers. We are going to be discussing like the convolutional and other LSTM and RNN layers in the subsequent videos. Okay, now let's turn to the concept of an activation and how does it impact the training. So what we are going to do is let's begin with the imports quickly. What we'll do is we'll also generate a circles data set using the scikit-learn. So that is what, so basically there will be two sets of points here and we will try to classify it. Now the first network that we are going to have actually is going to have only a couple of layers. Okay, so we have got only two dense layer here, and we are going to run like train this particular model onto the data that we have. Okay, so we already defined the data. Let's define this model and run the training. It's going to take a little bit of time, so I'm going to so our training is complete, and the results that we see is train is 0.782 and test is 0.780, right? So looks okay, but not that great, right? So is there any way to improve this? So what we do here is we are going to be defining a deeper network. So we are going to have more layers, and just notice the activations also, they are tanh, and the weight initialization is random uniform. So we'll try out this strategy also and try to see if this is going to improve. Okay, or let's see what happens. Okay, so same data set, a different network, right? So in this particular case we just had like two layers. We use the activation tanh and the weight initialization as a random uniform, and in the final layer we just use the sigmoid. Okay, so in this case also the same thing, tanh sigmoid, same random uniform, weight initialization also. Okay, so let's run this and see the results. So as you can see, if you compare the results of this particular network, is 0.782 the accuracy and 780. Now as we made the network deeper, actually it has become worse, right? It has gone bad because now the accuracy is just 0.546, 0.504. So changing the network, like making it deeper, actually worsen the problem. Okay, the reason it may be because of the vanishing gradient, because the tanh and the sigmoid, they're kind of prone to this vanishing gradient problem. So that might be because of it. Okay, so let's change that. So what we will do is we'll change the activation to ReLU, and we'll change the weight initializer to He uniform, and we'll do the same thing for all the layers, and the final layer we are just going to keep as sigmoid. Okay, so let's see. Let's run this and just check this out. So well, the training is done, and the results, we have the accuracy 0.830, 0.820, uh, and this is what we had earlier, right? The deeper network, but a different set of activations and initializers, and we here we just change the activation and the initializer, and improvement in the results, right? So just keep this in mind, that the right activation and the right initializers, they are pretty much important, and usually, as we discussed earlier, the He uniform goes with the ReLU, and with the tanh usually we can go with like Xavier uh, initialization. That's what we typically do. Okay, let's see the next notebook also. Let's begin with the input. We'll see the effect of the batch normalization in this particular case. So the first example here is without the batch normalization. So let's quickly run this. So the training is complete, and it took more than 2 minutes and a few seconds. as you can see, it's a case of overfitting because the training accuracy is already saturated to 1. The test accuracy is kind of flattened. In fact, it reduced actually. So it definitely is a case of overfitting, right? Now, can we improve this? So what we do here, we just introduce this batch normalization layer here. Rest of the things are all the same, and we are going to run this and see if we are able to get any better results. Okay, so here are the results. Basically the model trained in less than say 15-20 seconds, and as you can see, the training accuracy and test accuracy are pretty close. So it definitely solved the overfitting problem. So what we changed, only we introduced this batch normalization between the two layers, right? So that kind of resolved this particular issue of overfitting without it, right? So that's pretty much we have as far as the notebooks are concerned. Let me quickly go to the summary, and we will see what we learned. So in this session, what we discussed, we talked about the core layers, Keras core layers, and they included input. We saw flatten and reshape. We talked about dense also, and while we were talking about dense, we saw what the activation, what are the different kind of activations, and what is the impact of choosing each one of them. And we also saw that uh, the scheme of initializing the weight also makes a difference uh, in terms of speeding up the training, and there are certain activations or certain initialization schemes that kind of go hand in hand. And we also talked about two things: how to take care of this overfitting and vanishing gradients using the dropout and the batch normalization, right? So that was pretty much for this particular video. So if you have any comments, any thoughts, please let me know through your comments. And once again, thank you so much for listening to the video, and I'll be back with some more videos. Thank you so much. Bye bye.